So far, we've looked at what happens when the temperature changes and the kinetic energy changes inside a body. Now we're going to look at what happens when the potential energy changes. And to do this, we're going to look at a liquid which has a melting point of 69 degrees. And we've heated it to above 90. So what's going to happen is that with time, it's going to cool down. It will cool down because it is warmer than the surroundings. So let's see carefully as this liquid cools down. The temperature goes down and down and down. But at this point, strangely enough, it's warmer than surroundings, so it must be losing thermal energy to the surroundings, but the temperature does not change. The internal energy must be going down because it's losing energy, but the temperature does not change. Then after a while, the temperature will start to go down again. So this is the melting point, 69. And when it changes from a liquid to a solid, during the phase change, the amount of kinetic energy per particle doesn't change, but still the internal energy must be going down because it's losing heat to the surroundings. Therefore, the potential energy must be changing. When they looked at this, they realized that there was a kind of hidden energy there, and it was called the latent heat. So what happens in the first part, when it cools, the particles are losing kinetic energy, they're getting slower, and therefore this internal energy is lost to the surroundings. The potential energy of the particles is constant. In the middle section, however, when it changes state, the kinetic energy must be constant because the temperature is not changing. And if it's losing energy, then the potential energy must be reduced. Then in the last stage, it continues to cool, it loses its kinetic energy, and here again, the potential energy is constant. So this whole process basically explains that this mysterious hidden energy is lost to the surroundings, and this is what is called the latent heat. So we need to define the specific latent heat. This is the amount of thermal energy that is required to change the state of a unit mass, or in other words 1 kilogram, of a substance. When it goes from a solid to a liquid, we call this the latent heat of fusion. When it goes from a liquid to a gas, we call this the latent heat of vaporization. How can we develop an equation for this? L is the latent heat, so we use the letter L. It depends on, it's basically the amount of energy that is needed or is produced per unit mass, per kilogram. But we rearrange this, it's more often in this form. Delta Q is equal to mL. Compare this. Delta Q is equal to mc delta T. What are the differences between mL is equal to delta Q and mc delta T? Why are they different? So the melting or boiling of a substance, this is the change of state, this is where the latent heat comes in. So delta Q is equal to mL. Delta Q is the thermal energy transferred, m is the mass of the substance, L is the latent heat in joules per kilogram. And it's fusion for melting, vaporization for boiling. And what is happening here? The temperature is not changing. In other words, the kinetic energy of the particles is not changing. Therefore, the potential energy of the particles must be changing. So basically, the potential energy is increasing if you're heating. And it's basically changing state, it's changing from a liquid to a gas, for example. There's no change in kinetic energy because the temperature is constant. The temperature does not rise, and what is happening, the bonds are breaking. There's an increase in the potential energy as the particles are pulled apart. So it could be melting a substance or boiling a substance. Here are some examples. Water has got a latent heat of fusion of 3.33 times 10 to the 5 joules per kilogram. Vaporization is 22.6 times 10 to the 5. 7 times as much. Lead has a value of 0.25 times 10 to the 5 for fusion, and to make it vaporize, it's 8.7 times 10 to the 5 joules per kilogram. Notice that all these values for latent heats are very large, much bigger than specific heat capacity. Also notice that vaporization is more than fusion. And this is basically because it takes more energy to pull the particles completely apart from each other as it turns from a liquid to a gas than it does when it changes from a solid to a liquid. There are still some bonds in place. When it vaporizes, the atoms are pulled completely apart.